where do we go from now? Well, let's make a more general statement of the variational principle. Again, sometimes it's not all that convenient to have normalized wave functions. So recall that if psi of x is not normalized, psi of x over the square root of integral of psi squared dx is. Therefore, if you hand me an arbitrary psi of x that is really arbitrary, you didn't even bother to normalize it, then when I plug here, in this formula, it is supposed to be normalized, so I plug the second expression there. So therefore, I get that EGS less than or equal that integral of psi star h psi dx over integral of psi star psi dx. So this is actually nicer in one way, because you don't have to work with normalized wave functions, and that result must be true still. Yes? Sure, it cannot be completely arbitrary. The function should be normalizable. It doesn't have to be normalized, but normalizable. So here you got, and here let me introduce just a little name. F of psi. F of psi is what is called a functional. F is a functional. What is a functional? A functional is a machine or an expression whose input is a function and whose output is a number. So here, f of psi is a functional, and maybe I should use brackets. Many times people with brackets denote that, watch out, this is not a function, it's a functional. And here it is. You give me a, no dash there. You give me a psi of x, which is a function, and then this is a number, because you've done the integrals. So here, that is like the brachistochrone problem. That's the funny name for it. Here it is. There is a functional, which is the time that it takes to go here. You give me a path, a function, and I can calculate the time it would take the mass to get here. So this was the issue of finding a critical point of a functional. So actually, we start to see it. It seems that the ground state energy is the minimum of this functional. And what is interesting as well is that when you get the minimum, you will have gotten a ground state wave function. So the ground state wave function actually is the thing that minimizes this functional and gives you as a value the ground state energy. A little more in a couple of minutes. Let's do an example. How do we use this? So now, if you think about this carefully, it's kind of dizzying, because what is a functional really is, in some sense, a function in an infinite dimensional space. Because a function itself is specified by infinitely many numbers that you can change. So, you know, how many dimensions you have is how many ways you can move your hand that are linearly independent. But if you have a function and you can change it here, or you can change it there, or you can change it there, or there, and those are all orthogonal directions. So you're finding a critical point. So when you find a critical point, you should imagine that you're plotting a function that is not one-dimensional function or two-dimensional function, but it's infinitely dimensional function, direction 1, direction 2, direction, infinitely many directions, and suddenly in this infinitely many directions you find a critical point. It's really incredible that one can do these things. So you're at that critical point and you can deform the energy eigenstate by making it a little fatter here or thinner here or up there, and those are the infinite directions. In any direction that you move, the energy goes up because you're at the global minimum. It's pretty amazing. Something that you will prove in the homework is that actually it's even more. Every single eigenstate is a critical point of this functional. So you got the lowest energy state, and in that infinite dimensional space, in every direction that you move, you go up. The first excited state is another critical point, but it will not be an absolute minimum. It will be a saddle, an infinite dimensional saddle, in which there are infinitely many directions in which you go up. There's one direction in which you go down because you could flow towards the ground state. So the first excited state is a saddle, but these are all stationary points of this functional. So we'll conclude by doing this example. One second, example. Sorry, what is the question? I didn't assume it's non-degenerate. So if you have two things that have the same ground state, the functional will have, in fact, a degeneracy. There will be two solutions that have the same energy, and any linear combination of them will have the same energy. So the proof that I did here doesn't assume non-degeneracy. It's even true with degenerate things.